Astronomers have discovered the second closest black hole to Earth, named Gaia BH3. However, this black hole is nearly 3.5 times larger than the closest black hole discovered to date, placing it in a category of black holes that, under our current understanding, should not exist. At least this is the case within the framework of what we initially knew about these specific types of black holes. This discovery raises an intriguing question. If such a massive black hole has been right under our noses and we missed it for so long, what other unknown black holes could be lurking out there? Let's dive in and learn more. First and foremost, this incredible discovery was not made by NASA, but by the European Space Agency, ESA, using the Gaia Space Observatory, which was launched in 2013. Much like the famous James Webb Space Telescope, Gaia orbits around a special gravitational region known as the L2 Lagrange point. This is one of 5 special gravitational zones created by the interaction of the Sun and Earth's gravitational fields. Gaia orbits around the L2 point, which lies about 1.5 million kilometers on the far side of Earth from the Sun. Since the beginning of its mission, Gaia has achieved remarkable successes. For example, out of the 400 billion stars in the Milky Way galaxy, Gaia has successfully cataloged 1.7 billion with high precision. Thanks to Gaia, we continue to discover new exoplanets, galaxies, and stars every year. Typically, astronomers prefer to compile all this celestial data into a catalog and release it every 3 or 4 years, rather than publishing each individual finding separately. For instance, Gaia's latest data catalog was published in 2022, with the next one expected in 2025. But the discovery of Gaia BH3 is so significant that astronomers chose to publish a paper on it without waiting for the next catalog update. Immediate research on this black hole is crucial. Despite Gaia BH3's extraordinary size, it is actually one of the smallest black holes we've discovered so far because it's not a supermassive black hole, it's a stellar mass black hole. However, within this class, it has an unusually large mass, making it very special. As I've explained before, stars with a mass of 8 or more times that of the Sun reach the end of their life and explode in a massive supernova when they run out of fuel. During this explosion, they eject most of their matter and energy into space, and the remaining material compresses with such great force that it creates a massive accumulation of matter in a tiny volume. If this leftover matter exceeds the Tolman-Oppenheimer-Volkoff limit of 2 to 3 solar masses, the star's core continues to collapse into the most mysterious object in the universe, a black hole. If the leftover matter is below this limit, a neutron star forms instead. However, there's something less well known. Just as there is a minimum mass required for a star to collapse into a black hole, there is also a maximum mass. If a dying star is exceptionally large, the processes that are weaker in smaller stars occur much more intensely, preventing the star from collapsing into a black hole. For instance, if a star is very large and also has high metallicity, meaning it contains a high proportion of atoms heavier than hydrogen and helium, it produces powerful stellar winds. These winds cause the gases in the star's upper atmosphere to be blown away at high speeds into space. Just like planets, stars have atmospheres, and the activity in these atmospheres can determine a star's fate, much like Earth's atmosphere influences its destiny. Additionally, other factors, such as the extremely high-energy radiation produced by large stars, the currents caused by the millions of degrees temperatures in their coronas, and coronal mass ejections caused by the movement of their magnetic fields, similar to the solar flares on our Sun, can cause these winds to reach speeds of hundreds or even thousands of kilometers per second, allowing atoms in the star's atmosphere to escape its gravitational pull and be hurled into space. Because of all these factors, very large stars, especially those near the end of their lives, lose so much mass through these mechanisms that they cannot produce supernovas large enough to form massive black holes after their death. Moreover, stars between 130 and 250 times the mass of the Sun can experience a phenomenon known as pair instability supernova. In these extremely large stars, the core becomes so hot and under such high pressure that thermal photons spontaneously create electron-positron pairs. These pairs steal the energy of the photons, which weakens them and causes the core to become increasingly unstable. Supernovas occurring in stars with weakened cores are so destructive that nothing is left to form a black hole. All the material is ejected into space. For all these reasons, it has long been thought that the maximum mass for stellar black holes formed by the death of a star should be around 20 solar masses. Anything larger shouldn't be possible. Yet Gaia BH3 has a mass of 32.7 solar masses, far exceeding this limit, which is why I initially referred to it as a black hole that shouldn't exist. However, Gaia BH3 is not the first abnormally large stellar black hole we've discovered. If you recall, the biggest science news of 2015 was that the LIGO interferometer detected gravitational waves emitted by the merger of two black holes. That discovery was indeed one of the most remarkable predictions of Einstein's general theory of relativity. Yet one important detail that wasn't sufficiently emphasized or understood in those reports was that the black holes involved in the merger had masses of 29 and 36 solar masses, respectively. Notice that both of these masses exceed the 20 solar mass upper limit predicted for stellar black holes. Although Cygnus X1, with a mass of 21 solar masses, had already hinted that this could happen, it didn't challenge the existing theory enough to cause serious concern. LIGO's 2015 findings clearly showed us that something was amiss. Understanding how these stellar black holes form is crucial because we know very little about how supermassive black holes like Gargantua from Interstellar or Sagittarius A at the center of our Milky Way galaxy are formed. These black holes aren't just 20 or 30 times the mass of the Sun. In the case of Sagittarius A, we're talking about 4 million times the mass of the Sun, with other examples reaching billions of solar masses. These enormous black holes likely start their lives already at absurdly large sizes, probably formed by the direct collapse of metal-poor, supermassive stars without ever undergoing a supernova. Over billions of years, they grow to colossal proportions by merging with other black holes and consuming surrounding matter. But research on this topic is ongoing. Although today's focus is on Gaia Black Hole 3, or Gaia BH3 for short, which is not a supermassive black hole, it is nonetheless just as fascinating and surprising. This stellar black hole, nearly 33 times the mass of the Sun, is only 1,930 light-years away from us. And here we are, only just now discovering such a massive black hole that is so close to us in astronomical terms. Now, to be clear, 1,930 light-years is still an immense distance, about 2% of the distance from one end of the Milky Way to the other. So there's almost zero chance that we'll wake up one morning and find ourselves face to face with this black hole. Even if we were traveling toward each other at the speed of light, which we aren't, it would take around 1,000 years for us to reach the same point. That said, while Gaia BH3 may not pose a significant risk to our lives, it is still worth noting its astronomical value. It's the second closest black hole we've discovered so far, with Gaia BH1, a black hole 9.5 times the mass of the Sun, being just 1,560 light-years away. Even though BH1 is closer, BH3 remains the second closest black hole we've found, located in what could be considered the backyard of our galaxy home. Who knows what other black holes we might be missing in this region? More importantly, the discovery of an absurd black hole like Gaia BH3 is helping us better understand the conditions under which stars much larger than 20 solar masses can collapse into stellar black holes. One of the factors contributing to this is the star's metallicity, or the proportion of atoms heavier than hydrogen and helium. The lower the metallicity, the less the star is affected by stellar winds. Additionally, the interactions between stars before they die also influence the characteristics of the resulting black hole. For example, in binary star systems, one star may strip the outer layers of the other, reducing its mass and allowing it to collapse into a black hole. And Gaia BH3 is indeed part of a binary system. One of the objects is this black hole, and the other is a red giant star, which is very large, very bright, and, interestingly, also metal-poor. In fact, the presence of this red giant is what enabled us to detect Gaia BH3. Since black holes do not emit any light, with the possible exception of Hawking radiation, they are nearly invisible in the darkness of space. Therefore, to detect them, we look for anomalies in the orbits of nearby bright stars. If a star is orbiting something, but we can't see what it is, this suggests there might be a black hole. We then study the deviations in the star's path to calculate the mass of the object it's orbiting. Finally, we focus our observation tools on that point to confirm the presence of a black hole using gravitational lens. Gravitational lensing techniques, confirming that there is indeed a black hole at that location. Gaia BH3 appears to be relatively clean of any accretion disk, meaning there isn't a noticeable buildup of material being drawn into the black hole. This lack of visible accretion disk may be why it took so long to detect. This clean nature of Gaia BH3 suggests it formed much earlier, before it had the chance to trap its companion star in orbit. The companion star, which is a red giant, was formed at most 2 billion years ago. Therefore, Gaia BH3 must have formed even earlier. Even though our Milky Way galaxy formed only a few 100 million years after the Big Bang, it wouldn't be too far off to say that this black hole has witnessed the infancy of our galaxy. Interestingly, the star in the BH3 system rotates in the opposite direction to most stars in the central disk of the Milky Way. This, combined with its ancient age, suggests that this binary system likely did not form within our Milky Way galaxy. Instead, it might be a visitor from another galaxy. This isn't entirely surprising, as we know our galaxy has collided with many neighboring galaxies throughout its history. For instance, about 11 to 8 billion years ago, a collision with a dwarf galaxy known as Gaia Sausage brought many stars into the Milky Way. The name Gaia Sausage comes from the fact that this galaxy was detected by Gaia, and because the star velocities it contributed to resembled a sausage-like distribution. In conclusion, this mysterious black hole might have been carried into our galaxy from another galaxy due to such cosmic collisions and now resides in a relatively close orbit to us by chance. As we continue to learn more about Gaia BH3, thanks to the dedicated efforts of astronomers, we will undoubtedly uncover more details in the years to come. By the way, if you don't want to miss out on future videos, be sure to activate channel notifications now. Also, if you enjoyed this video, I recommend watching our video on 10 things you didn't know about black holes to learn even more. See you in the next video, and take care.